Hello everyone, welcome to Circuit Insights. In this video, we are going to understand some of the fundamental electronic components that are used in almost every modern electronic device. But instead of just learning what these components are, we will first understand the problems engineers faced in electronic circuits and why these components were invented to solve those problems. And in this video, we will start with one of the most important components in electronics, the capacitor. Before understanding the capacitor, we first need to understand what a signal is. In simple terms, a signal is a voltage that changes with time. Many people think DC is also a signal, but technically, DC is not a signal. DC voltage remains constant with time, which means it does not change. Since a signal must vary with time, DC does not satisfy the definition of a signal. Now let us look at AC. AC stands for alternating current. In AC, the voltage continuously changes with time. Because the voltage varies with time, AC can be considered a signal. However, most modern electronic devices such as computers, mobile phones, and digital circuits require DC voltage to operate. So we convert AC into DC called rectification. The process of converting AC into DC is called rectification. There are two types of rectification: half-wave rectification and full-wave rectification. But even after rectification, the output is not a perfectly smooth DC voltage. Instead, we get pulsating DC which still contains small fluctuations called ripples. These ripples can create problems in electronic circuits. So the next question is, how do engineers remove these ripples and produce a smooth DC voltage? To fix this problem, electronic circuits are designed to work with a fixed DC voltage. Engineers choose a specific voltage so that all the components in the circuit work properly and predictably. If the DC voltage keeps fluctuating, the components may not behave as expected, and the circuit may not work correctly. For example, consider an audio amplifier. An amplifier is designed to increase the amplitude of an audio signal using a specific DC supply voltage. If the supply voltage fluctuates, the amplifier cannot amplify the signal correctly. As a result, the audio signal becomes distorted and unwanted noise may appear in the output. So to make circuits work reliably and to keep signals clean, electronic devices require a stable DC voltage. Because electronic circuits need a stable DC voltage, engineers needed a component that could store and release energy when required. This led to the development of a capacitor. A capacitor consists of two metal plates separated by an insulating material called a dielectric, such as ceramic. When the capacitor is connected to a battery, the plate connected to the negative terminal receives extra electrons and becomes negatively charged. The other plate loses electrons and becomes positively charged. Now we may ask, how does the capacitor store energy? To understand this, imagine stretching a string or a rubber band. When it is stretched, energy is stored in it because it tries to return to its original shape. A similar idea happens in a capacitor. The positive and negative charges on the two plates naturally try to attract each other, but the dielectric material between the plates keeps them separated. Because these opposite charges are forced to stay apart, energy is stored in the electric field that forms between the plates. In this way, a capacitor stores energy in the electric field between its plates. So I want to tell you that how these capacitors would help to processors present in computers and laptops, that is. Inside a computer or laptop, the CPU contains billions of transistors that switch on and off very quickly. When many of these transistors operate at the same time, they suddenly draw a large amount of current. This sudden demand for current can cause a temporary drop in the supply voltage. This effect is called a transient voltage drop. If the voltage drops too much, the circuits inside the CPU may not work properly. To prevent this problem, engineers place capacitors near the CPU on the motherboard. These capacitors store electrical energy and quickly release it when the circuit suddenly needs extra current. By doing this, capacitors help maintain a stable voltage supply so that the circuits inside the CPU can function reliably. In this circuit, we have a battery, a capacitor, a resistor, an LED, and a two-way switch. In charging phase, when the switch is in the charge position, the switch connects the battery directly to the capacitor. Electrons from the negative terminal of the battery move to one plate of the capacitor. That plate becomes negatively charged, and the other plate becomes positively charged. As the capacitor charges, its voltage gradually increases until it becomes almost equal to the battery voltage. In discharging phase. Now the charged capacitor behaves like a small power source. Electrons from the negative plate of the capacitor flow through the resistor and the LED toward the positive plate. Because current flows through the LED, it glows for a short time. As the capacitor releases its stored energy, its voltage gradually decreases until it becomes zero. How the battery gets disconnected. When we move the two-way switch to the discharge position, the internal metal contact inside the switch changes its connection. In this new position, the path between the battery and the capacitor is physically opened, so the battery is no longer connected to the circuit. At the same time, the switch creates a new path between the capacitor and the LED with the resistor. So the switch breaks one path and creates another path. Now let us see how a capacitor helps in ripple filtering using a bridge rectifier. First, look at the waveform without a capacitor. The bridge rectifier converts AC into DC, but the output is not a smooth DC voltage. Instead, we get a pulsating DC signal. The voltage continuously rises and falls. These variations in the DC output are called ripples. This is called ripple voltage. Now look at the waveform when a capacitor is connected across the load. The capacitor charges when the rectified voltage rises to its peak. When the voltage starts to drop, the capacitor slowly discharges and supplies current to the load. Because of this charging and discharging action, the capacitor fills the gaps between the peaks of the waveform. As a result, the large fluctuations in the voltage are reduced. The output voltage becomes much smoother compared to the waveform without the capacitor. So the capacitor acts as a ripple filter and converts pulsating DC into a smoother DC voltage. In simple, the capacitor stores energy at the peaks and releases it when the voltage drops, helping to smooth the DC output. Now let us understand how a capacitor helps in selecting high-frequency signals in a radio receiver. First, we need to understand the difference between high-frequency and low-frequency signals. A high-frequency signal means the voltage changes very fast with time. A low-frequency signal means the voltage changes slowly with time. First, consider low-frequency signals. Low frequency means the voltage changes slowly with time. Because the voltage changes slowly, the capacitor gets enough time to charge. Its voltage quickly becomes almost equal to the source voltage. So what happens? Since the capacitor voltage becomes almost equal to the source voltage, there is almost no potential difference across it. And we know one basic rule: current flows only when there is a potential difference. So, because the potential difference becomes very small, almost no current flows through the capacitor. That is why we say, for low-frequency signals, the capacitor behaves almost like an open circuit and blocks the signal. Now consider high-frequency signals. High frequency means the voltage changes very fast with time. Because the voltage changes very fast, the capacitor does not get enough time to fully charge. Its voltage cannot catch up with the source voltage. So what happens? There is always a potential difference between the source voltage and the capacitor voltage. Because of this potential difference, current continuously flows through the capacitor. That is why we say, for high-frequency signals, the capacitor behaves almost like a short path and allows the signal to pass. In this circuit, the capacitor allows high-frequency signals to pass, but how we select only one specific frequency from many signals, using an inductor and a capacitor together, will be explained in the next video. In this video, we focused on understanding the capacitor and its applications. In the next video, we will explore the inductor and see how the LC resonance circuit helps in selecting a specific frequency in radio receivers. If this video helped you understand the concept, please like the video, subscribe to the channel, share it with your friends, and drop your questions in the comments.